So today we shall continue with prime modulus, and you take p to be a prime number and consider the congruence fx congruent to 0 mod p. So if fx congruent to 0 mod p is a polynomial congruence and we assume that degree of the congruence is bigger or equal p, then it may happen that every integer is a solution to the congruence fx congruent to 0 mod p, or you can get a polynomial gx of degree less than p such that gx is monic and fx and gx have the same solutions. Examples of such polynomials which are reducible are, let us take x raised to 10 minus x plus 2 congruent to 0 mod 7. This is a congruence of degree bigger than 7. You can reduce it to a polynomial congruence of smaller degree by using the polynomial x raised to 7 minus x, which is satisfied by every integer. So just write this as x raised to 3 into x raised to 7 minus x. So this becomes x raised to 10 minus x raised to 4 plus x raised to 4 minus x plus 2. And then this polynomial and the original polynomial, they have the same solutions. So the congruence is equivalent to a congruence of smaller degree smaller than 7, namely x raised to 4 minus x plus 2 congruent to 0 mod 7. Any solution of this will be solution of this. So the method is that you use the polynomial x raised to p minus x, which is satisfied by every integer. Also, if you have a polynomial congruence which has n solutions, rather which has degree n, okay, so fx is bn x raised to n plus etc., and you assume that the degree of the congruence is n, that means bn is not congruent to 0 mod p, then the congruence has at most n solutions. In fact, the polynomial can be of higher degree as a polynomial, but degree of the congruence is suppose n. So you can just rephrase this. If fx congruent to 0 mod p prime is a polynomial congruence of degree n. Degree of the polynomial may be higher, but degree of the polynomial congruence is n. Then it has at most n solutions. This is true when the congruence is with respect to a prime modulus, but as we know from examples, this is not true for congruences with composite modulus. A corollary of this is the following. So suppose we have a polynomial congruence of degree n, and suppose it has more than n solutions, then what will happen? It means that all the coefficients of the polynomial are divisible by the prime p. Okay, that is the conclusion. So if fx is a polynomial of degree n and fx congruent to 0 mod p prime has more than n solutions. This is the congruence. The congruence has more than n solutions. Then all coefficients of fx are divisible by p. All coefficients of fx are divisible by p. The proof is that if some coefficient of fx, okay, one of the coefficients of fx is not divisible by p, then you can talk of degree of the congruence fx congruent to 0 mod p, and the largest degree coefficient which is non-zero mod p will give rise to the degree of the congruence. But in any case the polynomial is of degree n, therefore the degree of the congruence is less than n, less than or equal to n, we can say. So has degree, congruence has degree, and it is less than or equal to n, and therefore number of solutions of the congruence must be less than or equal to n. Because number of solutions of the congruence is at most equal to degree, when degree is there. Now it is given that the congruence has more than n solutions, so we get a contradiction. This is a contradiction to the assumption. That number of solutions is more than n, more than the degree. That means that all the coefficients must be divisible by p. Hence, all the coefficients of fx are divisible by the prime p. Now we shall see that for functions from residue classes mod p to residue classes mod p, these functions can always be considered as polynomial functions. So that is our next result. Theorem. If fx is a function that takes residue classes mod p to residue classes mod p, that is, in other words, we can say that it's a function from a complete residue system mod p to a complete residue system mod p. That is, f is a function from a complete residue system mod p to a complete residue system mod p. Like 0 to p minus 1, this is a complete residue system mod p to 0 to p minus 1. Then such a function can always be given by a polynomial. Then there is a polynomial fx such that fx is 0 or degree of fx is less than p and capital F of x is congruent to small f of x mod p for every residue class mod p. For every residue class mod p. So to prove this, consider gx equal to the polynomial 1 minus x minus a raised to p minus 1. Now if I put here x equal to a, what do you get? You get the value as 1. And if I put something which is other than a, modulo p, Then this is non-zero mod p, then raised to p minus 1. So by Fermat's little theorem, this is 1 mod p. And 1 minus 1, so that is 0 mod p. So then g of any x, or let us say g of b, is equal to 1 if b takes the value a, and it is 0 mod, this is mod p. If b not congruent to, you can say here congruent to a mod p, and not congruent to a mod p. And this is GB is, you can say, congruent to 1 or 0 modulo p. So GB is congruent to 1 mod p if b congruent to a mod p. GB is congruent to 0 mod p if b is not congruent to a mod p. This is what happens for the function gx. Now we define the polynomial like this, that define fx equal to summation, but let me write this function 1 minus such a function x minus I raised to p minus 1. Okay, now let us see what is the value of f j. So I equal to j, if you consider, then this will become 0, I minus I, and I is varying. So the term fj, that will survive when I is equal to j. So let me x equal to j. So when the value of I becomes equal to j, that will be fj, and all other terms will become 0. So it is f of j. Since for I taking the value j, 1 minus j minus j, that raised to p minus 1, that is 1, congruent to 1 mod p. And other terms, when I is not equal to j, they become 1 minus 1, so 0 mod p. For I not equal to j, 1 minus j minus I, p minus 1 is inside, sorry, p minus 1 is inside. So raised to p minus 1, this is congruent to 0 mod p. So one term survives and small fj equal to capital Fj. So the point is that if you consider general functions, from residue classes mod p to residue classes mod p, they are always polynomial functions. So it is sufficient to study polynomial functions when you want solutions of such functions mod p. So here equality means actually congruence, congruence mod p. The next thing that we will study is when is it that a congruence fx congruent to 0 mod p has exactly n solutions. So let fx equal to x raised to n plus an minus 1 x raised to n minus 1 plus etc. plus an, then fx has fx congruent to 0 mod p has exactly n solutions if and only if n is less than or equal to p and there is a monic polynomial gx of degree n minus p and a polynomial sx with integer coefficients such that we can write x raised to p minus x equal to fx into gx of degree p minus n. Here I should say p minus n. X raised to p minus x equal to fx into gx plus p times sx. And we describe this by saying that or in other words, fx is a factor of x raised to p minus x mod P. Fx is a factor of x raised to p minus x mod P. So you see that modulo P, this part is 0 and Fx will appear as a factor of this. It is not actually a factor, but modulo P you can say it is a factor. Okay, proof of this. So, first of all, if you assume that congruence has n solutions, then number of available elements in a complete residue system is P. So number of solutions is n, means n has to be less than or equal to P. So that part is clear. So since a complete residue system mod P has just P elements, if Fx congruent to 0 mod P has n solutions, that means there are n incongruent elements, n must be less than or equal to P. So the degree of the polynomial is less equal P. Now Fx is a monic polynomial and we divide x raised to P minus x by Fx and get a quotient and get a remainder. Assume that Fx congruent to 0 mod P has n solutions, where n is the degree of Fx. Divide x raised to P minus x by Fx and write x raised to P minus x equal to Fx into Gx plus Rx, where Rx equal to 0 or Rx is a polynomial of degree less than n. Either it is 0 polynomial or it's a polynomial with integer coefficients of degree less than n. N is the degree of Fx. Okay, now every solution of Fx is already a solution of left hand side and it must be a solution of Rx congruent to 0. Every solution of Fx congruent to 0 mod P is already a solution of x raised to P minus x congruent to 0 mod P. and hence it is a solution of Rx congruent to 0 mod P. If Rx is already 0, identically 0, then that's fine. If Rx is a non-zero polynomial, Rx congruent to 0 mod P is, it will be congruence of some degree. Degree is less than n, provided some coefficient of Rx is not divisible by P. If some coefficient of Rx is not divisible by P, then we can say that this is a congruence of some degree. That degree is less than n. But fx congruent to 0 mod P, it has n solutions. And every solution of fx congruent to 0 mod P is a solution of Rx congruent to 0 mod P. Therefore, this congruence has n solutions at least. And it has at least n solutions. So this is a congruence, Rx congruent to 0 mod P is a congruence for which the number of solutions is more than the degree of the congruence. Hence, for the congruence, Rx congruent to 0 mod P, the number of solutions is bigger than the degree of the congruence. This is a contradiction, or because then Rx will be okay. So all coefficients of Rx are divisible by P. If all coefficients of Rx are divisible by P, we can write Rx as P into some polynomial Sx. We can write Rx equal to P times Sx for some Sx in Zx. This is a polynomial with integer coefficients, and therefore x raised to b minus x equal to fx into gx plus p times sx. Thus fx equal to this x raised to p minus x is equal to fx gx plus p times sx. That's what you want. This is one part actually, that if fx has n solutions, then you get a monic polynomial gx of degree p minus r. See that when you use this division method, the quotient gx is again a monic polynomial of degree p minus r. So let me write that part, that note that in the division process, fx equal to x raised to p minus x equal to fx gx plus rx. If you compare the coefficients of fx gx and the left hand side, here the coefficient of x raised to p here it is 1 equal to coefficient of fx is of degree n in fx multiplied by, this is gx, which is a polynomial of degree n minus p, so coefficient of x raised to n in fx is already 1, and this coefficient therefore is also 1. So in the division algorithm we get this polynomial of degree, this is what, p minus n, this is p n, so p minus n. So gx is of degree p minus n and its leading coefficient is 1. That is what is also a part of this. Conversely, you assume that x raised to p minus x equal to fx into gx plus p times sx, where gx is monic of degree p minus n. Conversely, assume that x raised to p minus x equal to fx into gx plus p times sx. Here gx is monic of degree p minus n, and sx is a polynomial in zx. polynomial with integer coefficients. Then if you take any solution of fx, then it's a solution of x raised to p minus x. That's right there, because all the elements say 0 to p minus 1, they are solutions of this, or all elements from a complete reduced system are solutions of this. Now if you take the n solutions of fx, so we have to show that there are exactly n solutions. Okay. Every solution of x raised to p minus x congruent to 0 mod p, it is solution for the right hand part, and this has p solutions, and that let us use. Now every solution of x raised to p minus x congruent to 0 mod p is the solution of fx into gx congruent to 0 mod p. Because this is 0 for any value of x. So any solution of x raised to p minus x congruent to 0 mod p is a solution of this. But fx congruent to 0 mod p has at most n solutions, because fx is a monic polynomial of degree n and the modulus is a prime, so this can have at most n solutions because n is the degree of the congruence, and gx congruent to 0 mod p has at most p minus n solutions, because that is the degree of the congruence. P minus n is the degree of the congruence gx congruent to 0 mod p, because gx is monic. Gx is monic of degree p minus 1. Now if fx into gx is congruent to 0 mod p, that is p divides fx into gx for a solution x, so p should divide either fx or p should divide gx. So for a solution of fx into gx congruent to 0 mod p, that solution must be either a solution of fx congruent to 0 mod p or a solution of gx congruent to 0 mod p. Also, since p is prime, any solution of fx gx congruent to 0 mod p is a solution of fx congruent to 0 mod p or gx congruent to 0 mod p. Now look at the scenario. We have p solutions of fx x raised to p minus x congruent to 0 mod p. all these are solutions of fx congruent to fx into gx congruent to 0 mod p. Solutions of fx into gx congruent to 0 mod p are either solution of this or solution of this, because p is prime. This has how many solutions? At most n solutions. This has at most p minus n solutions. Total solutions are p. So number of solutions of this must be the number n, which is the degree of this, and this has to be p minus n. Solutions for gx congruent to 0 mod p must be p minus n, otherwise you will get less number of solutions. So number of solutions of fx congruent to 0 mod p must be how much? Must be n. Must be n, and number of solutions for the other one, and number of solutions for gx congruent to 0 mod p must be p minus n. That's what we wanted. That if we have x to u minus x equal to fx into jx plus p times sx, then this fx is of degree n, that is given to you, fx will have exactly n solutions. So this is a criterion for the congruence fx congruent to 0 mod p to have exactly n solutions, where n is the degree of the congruence as well as degree of the polynomial. The polynomial is a monic polynomial, and this is what we shall be using in the